chi-square distribution. So chi-square distribution. So first we know that we have z squared is equal to chi-square distribution with degrees of freedom 1. And there are several types of standard normal. Okay, so first is this x minus mu x divided by sigma x. Okay, so this square is chi-square distribution with degrees of freedom 1. And also this one is chi-square distribution, x bar minus mu x, and divided by sigma x squared divided by n. Of course, we have to get square here. It is also chi-square distribution with degrees of freedom 1. And for chi-square distribution, it has a very special property. So let us say U is a chi-square distribution with degrees of freedom V1, and V is another chi-square distribution with degrees of freedom V2. And if you have U plus V, then it's going to be chi-square distribution with degrees of freedom V1 plus V2. Okay? And last time we have shown this property, so we already know this is true, right? We already know this is the case. Standard normal square is equal to chi-square distribution of degrees of freedom 1. And we know that, okay, you're going to check your note. We showed this last time. N minus 1 sx squared divided by sigma x squared. This is a chi-square distribution with degrees of n minus 1, degrees of freedom n minus 1. And this one, okay, summation xi minus mu x squared sigma x. This is chi-square distribution with degrees of freedom n. Okay. The reason is because for each of them it is a standard normal square, right? It is a standard normal square, and how many do we have? You have n, so it is degrees of freedom n. Because each one is degrees of freedom 1, and you have total number of n. But this one, okay, it takes a little time to prove it, okay? And last time we did, okay, we did it. So you want to check your note to see how to get this. And when we get to the notation of chi-square distribution, it is how to denote a chi-square distribution. So we have here, okay, suppose it is something like this, okay? This is f chi-square with degrees of freedom v, okay? Usually we denote it like this. So if this is alpha, okay, if this is alpha, then this one is denoted as chi-square with degrees of freedom v and alpha. Okay? Then what about here? Suppose here it is alpha. Okay, if this is alpha, then how to denote this? Because if this part, the probability of this part is equal to alpha, that means this part to the right, okay, this part to the right, it is 1 minus alpha. So it is chi-square degrees of freedom v, 1 minus alpha. Okay, so this time we showed this before. So this is the random variable, chi-square degrees of freedom v, greater than or equal to chi-square degrees of freedom v, alpha. It is equal to alpha. Okay? And what about this? P chi-square degrees of freedom v less than or equal to chi-square degrees of freedom v alpha. What is this equal to? Mr. Chen. What is this equal to? One minus alpha, right? Okay. Okay, then the same thing, we're going to do this again. Okay, so what about here? P, okay, chi-square degrees of freedom v greater than or equal to chi-square degrees of freedom v 1 minus alpha. What is this equal to? This does it. 1 minus alpha. Okay? And what about this? Chi-square degrees of freedom V, where less than or equal to chi-square degrees of freedom V alpha. What is this equal to? Mr. Wu? Oh, sorry. But anyway, still, even I put down this, you can get it, but it should be here. Okay? That would be, so it's less than this part, right? So it is alpha. Okay, so basically you need to take care of all these notes. Okay? A different kind of notation, a new distribution, a different kind of notation. And of course, generally, chi-square distribution is skewed to the right. Okay, skewed to the right. But as the degrees of freedom increases, okay, as V increases, okay, so let's say like this, what is going to happen? Chi-square distribution, okay, will approach Z distribution, that is standard normal, okay. So basically, if you know, okay, if you know the standard, if you know the degrees of freedom and it's very large, you can use standard normal to approximate the value of chi-square. And we have shown one example before. We have shown one example before. So please check your note. Okay, we have shown one example before. Okay, questions? Now what we're gonna do now is to try to get this T distribution and to find out the relationship between T distribution and chi-square distribution. So the time we're going to use T distribution is when the population variance is unknown. Okay, so we say if you know sigma x squared, okay, so x bar minus mu x divided by sigma x squared divided by n, this is equal to z, right? This is z distribution. But we say when you don't know the population variance, what you're going to do? You're going to use sample variance, right? So it is going to be T, okay? And of course, there's the degrees of freedom, okay? And let us say it is degrees of freedom n minus 1, okay? So let us say it is n, okay? So we have something like this. X bar minus mu x, okay, sigma x sx squared divided by n, okay. So generally, this is the formula. But as a matter of fact, this can be transformed to standard normal divided by chi-square and degrees of freedom. So let us say this is degrees of freedom V, and this is degrees of freedom. Okay? And now we want to show, how this one can be transformed to this one. And this is degrees of freedom n minus 1. Okay, this is degrees of freedom n minus 1. So degrees of freedom n minus 1. So suppose the sample size is n. If the sample size is n, the degrees of freedom is n minus 1. Okay, I believe we have talked about this before, right? If you have n sample size and this one is a known, but you know x bar, right? Then the degrees of freedom is n minus 1. Okay, so let us try how to show this. So how to transform this one into this one, and then to show the relationship between T distribution and chi-square and standard normal distribution. Okay, so we know T distribution degrees of freedom n minus 1 is equal to x bar minus mu x and sx squared divided by n. Okay? Any questions so far? Okay, then what we're gonna do? We're gonna do this. Okay? So first thing first. So this one, we're gonna X bar, because you're gonna transform this one into a standard normal. Okay? You wanna get this one into a standard normal. So how to get this one into a standard normal? X1 minus mu x, you have to divide it by sigma square over n, right? Because if you have this divided by sigma square, square root of sigma x squared divided by n, then it is standard normal, right? Okay, so the same thing here. This one, okay, sx squared over n divided by sigma x squared over n. Okay, so in this case, you divide the numerator and the numerator and the denominator with the same thing. So what you do? You divide it by 1. So it is the same. Okay? So what you're going to get? So the numerator here, okay, for the numerator here, you already get z. So this is exactly what's going on here. Okay? So this is already standard normal. And what about this one? This one is actually, okay, because n and n will be cancelled out. Okay, so what you have? You have sigma x, sorry. So then you have sx squared, okay, over sigma x squared. Right? And then what you get? This is z, okay, and here you have n minus 1 sx squared n minus 1 sigma x squared. Okay? Because I multiply the numerator by n minus 1 and I multiply the denominator by n minus 1, so it's still equal to each other, right? Okay, but then the question is, what is this? What is this part? This part is chi-square distribution with degrees of freedom n minus 1, right? So then you have z divided by chi-square distribution with degrees of freedom n minus 1. And what is here? This is n minus 1. Okay? And this is exactly equal to t distribution degrees of freedom n minus 1. Okay? Questions? Okay, if you don't have any question, we're going to get to estimation for the variance. Questions? Here. Because it is here. So you have sx squared divided by n, right? And divided by sigma x squared divided by n. Okay? And then you're going to change it. N sx squared. Division, you have to flip that. Okay? Flip flop. Okay, so you have to times it by sigma x squared divided by n, right? So if you divide it by 2, means what? Means you multiply by 1/2. Okay, so this is 2 and this is 1/2, right? Okay, you have to turn it upside down, downside up. Okay? Which one? Here. This one? You already turned it into z. You already turned this into z, right? So actually, you know, this is x bar minus mu x sigma x squared divided by n. So it is here, right? So what you need to do is the bottom part, okay, the the up part, okay? It is done here. So you don't deal with it here. You have to deal with it down here. Okay? And so this is what you get. So this proves that t distribution is related to chi-square distribution. Okay, and we just briefly mentioned that you have to deal with it again in the final examination about the difference of two population mean and the difference of two population proportions. And I just mentioned that suppose the two populations are independent, okay, very important, they are independent, sigma x squared, sigma y squared norm, okay, both of the variances are known, then just do as usual, okay? But suppose the sigma x squared, sigma y squared are unknown, but sigma x squared is equal to sigma y squared. In that case, you have to use sp squared. Okay, what is sp squared? So p squared is equal to nx plus ny minus 2, and here nx minus 1 sx squared plus ny minus 1 xy squared. Okay? And then the other difficult question is the interval estimation of two population mean, but the population are not independent, so the population are dependent. Then you have to get a new variable, that is d. Okay, it's going to be x I, so di is equal to xi minus yi, and then you're going to get d bar. Okay, actually that's summation di, okay, divided by n, and then of course you have sigma d squared, and then you have sd squared, right? Depending on, suppose this is a norm, then you have to use the simple variance to replace okay, the population variance. Okay? Any questions? Okay, now we're going to get to estimation of the variances. Okay, so interval estimation of variance. The same thing. So the first important thing is that you have to know this. N minus 1 xx squared divided by sigma x squared. This is a chi-square distribution of degrees of freedom n minus 1. Okay, this is what you need to know. And then you have probability, okay? Chi-square distribution with degrees of freedom n minus 1, 1 minus alpha over 2. That's going to equal to n minus 1 xx squared sigma x squared. That's going to equal to chi-square, okay, n minus 1, okay, alpha over 2. This is equal to 1 minus alpha, okay. So basically, if you look at the diagram, it's something like this, okay. So here it is alpha over 2, right, and here it is chi-square degrees of freedom n minus 1. Alpha over 2. And here, the same thing, right? Chi-square distribution n minus 1, here is 1 minus alpha over 2. So here you have alpha over 2, here you have alpha over 2. What is in between? In between, that is 1 minus alpha, right? So basically, this is what you get, okay? This is the random variable. The random variable between two values. This is the right-hand value. This is the left-hand value. So this random variable between these two values, the probability is equal to 1 minus alpha. Okay? just like, we say P, okay, Z, right? Less than Z alpha over 2, okay, and Z minus alpha over 2. And what is that equal to? 1 minus alpha, right? That is basically the same thing. Okay, basically that's the same thing. Questions? And now we're going to manipulate this formula and to see how to get the interval estimate. Remember how we deal with this. So this one is actually equal to x bar minus mu x and then sigma x squared divided by n, right? And then we manipulate this formula and then we get the result we have. So finally we know the mean must fall into a region with confidence interval of 1 minus alpha, and that is x bar plus minus z alpha over 2 times sigma x squared divided by n. Okay? And we're going to do the same thing. So this is the interval estimate, okay, interval estimation for the population mean. And now we are going to get the same thing, but it is for population variance. Okay, for population variance. And now let's try to work it out. So first thing first, if you look at this, okay, so this is what we have, okay, but of course we don't know anything about the population variance. So we are trying to figure out what's the relationship between the population variance and the sample variance. Okay, of course we would like to find out the information about population variance from sample variance. And so let us put this upside down. Okay, put this upside down, flip around here. So what you're going to get? First thing you've got to be very careful. So let us say 3 less than or equal to 4 less than or equal to 5, right? If you put it upside down, what happened? 1 over 3 greater than or equal to 1 over 4 greater than or equal to 1 over 5, right? So the direction has to be changed. Okay, it is the opposite direction. So now what we're gonna do is P, okay, because now we move it upside down, downside up. So you have, okay, here, chi-square degrees of freedom n minus 1, 1 minus alpha over 2, right? Greater than or equal to sigma x squared n minus 1 sx squared. Greater than or equal to 1 over chi-squared n minus 1 alpha over 2 equal to 1 minus alpha. Okay? Any questions so far? And now, because generally we put A less than or equal to B less than or equal to C, so then we will change the direction here. So what we end up is, and then, okay, we're going to multiply this. If you multiply 3 of them by n minus 1 times xx squared, then what you have? You're going to have, okay, n minus 1 xx squared, and then this chi-square distribution n minus 1, okay, alpha over 2. That's going to equal to sigma x squared. That's going to equal to n minus 1 xx squared x chi-squared n minus 1, 1 minus alpha over 2. So basically, it is very simple. So if the question asks you how to get a interval estimation for population variance, it is like this. And of course, you need to check the table to find out exactly what is the value of chi-square distribution n minus 1 alpha over 2. And this one, chi-square distribution of freedom n minus 1, 1 minus alpha over 2. But giving you table, it is a it is not that not that necessary. So as a matter of fact, if we have this kind of question in the final, okay, if we have this kind of question in the final, you don't need to calculate this, but you need to put down exactly what it is. Okay? You have to put down exactly, degrees of freedom, right? And then the probability here. So let us say alpha is equal to 5%. So alpha over 2 is 2.5%, and that will be 97.5%. And here will be 2.5%. So you need to put down the exact formula. Okay? You don't have to give me the number. But here you need to calculate it. Okay? The top part, okay, you have to calculate it. But for the bottom part, if you can put down the formula, that will be just fine. Let us take a break. As we discussed, you want to estimate interval estimation of the variance. So first thing you need to know, this formula, n minus 1 times xs squared divided by sigma x squared, it is a chi-square distribution with degrees of freedom n minus 1. And so from this, we know that the probability is equal to 1 minus alpha. And of course, after manipulating this formula, you know that to get an interval estimation for chi-square distribution, for the sample variance is like this. Okay, so when you put down the exam, you need to calculate this part because you should be able to know what is n minus 1 and what is xs squared. But for this part, you may simply put down the formula, but you need to specify, you need to tell me what's the degrees of freedom and what's the probability here. The percentage of the probability here, the same thing. This is when mu x is a norm. Mu x is population mean. So if population mean is a norm, you use this formula. But suppose population mean is norm. So if mu x is norm, then you need to use a different formula. Okay? So when mu x is norm, then you use x squared, right? And that is equal to 1 over n minus 1 summation xi minus x bar squared. But suppose mu x is norm. If mu x is norm, then you need to use sigma hat squared. And what is sigma hat squared? It is equal to 1 over n summation xi minus mu squared. Okay, so suppose it is mu x. Okay, then you need to use this formula. The reason we use this formula, it is quite simple. So let me erase this part here. So in this case, sigma hat squared is a new estimated. Okay, so this is a new estimated. The reason we use this one is because expectation sigma hat squared will be equal to sigma x squared. Okay, and let us show what's going on here. So you have expectation 1 over n summation xi minus mu x squared. Okay? And then this, if we're going to get this out of expectation, it is 1 over n. Okay? And then expectation summation xi squared minus 2xi mu x plus mu x squared. Okay? And then basically what you get, 1 over n expectation summation xi squared minus, okay? Here you have 2 mu x summation xi, and then plus summation mu x squared. Okay? Any questions so far? Okay, and what is this? This is actually n mu x squared, right? And here it is n mu x So you have minus, you have 1 over n summation, expectation, summation xi squared, right? And then minus 2n mu x squared minus plus n mu x squared. Right? Okay? So then what you have? You have 1 over n expectation summation xi squared. And what is this? This is actually x1 squared plus x2 squared plus xn squared minus n mu x squared. Okay. Now, can anyone tell me what is this equal to? So, Miss Light, what is this part equal to? So, what is this equal to? Expectation x squared. What is this equal to? Expectation x squared. Miss Dunn, what is this equal to? So, your turn. What is this equal to? What is this equal to? You know, if you forget about it, probably I'll see you next year again. What is this equal to? Mu x squared plus sigma x squared, right? So what you have? Here you have n, right? x1 squared to xn squared, right? So then you have a total of 1 over n mu x squared plus n sigma x squared minus n mu x squared, right? So this and this cancel out. And here you have n, here you have n, so that is equal to sigma x squared. Okay? So what does this mean? This means that if you know mu x, okay, if you know mu x, what you're going to use? You have to use sigma hat squared. And the reason we use sigma hat squared is because sigma hat squared is an unbiased estimator of sigma x squared. Okay, because it is unbiased. If at this point you're going to continue to use sx squared, right? What it's going to do? This will be biased. Okay, when mu x is known and you continue to use xx squared, then your result will be biased. Because now the unbiased estimator of the population variance is sigma hex squared. And what is sigma hex squared? It is equal to here. Okay, sigma hex squared is here. So now you know if the population mean is a known, the interval estimation for population variance is like this. Okay? The degrees of freedom is equal to n minus 1. N minus 1. But when the population mean is known, when mu x is known, then you have to use sigma hat squared. And the interval estimation for population variance will be this. It will be, okay, summation xi minus mu x squared, chi-square distribution, okay, degrees of freedom n, and here is alpha over 2, and then summation xi minus mu x squared, chi-square distribution, degrees of freedom n, okay, 1 minus alpha over 2. So there's a great difference between these two. When mu x is known, the degrees of freedom is n. When mu x is unknown, the degrees of freedom is n minus 1. Okay, and of course the numerator, it is different too. It is here and it is here. Okay? Questions? So now we finished classical distribution and the estimation of population variance. Now we will get to hypothesis test. Okay? So for hypothesis test, there are several things you need to know. First of all, it is nothing new. Okay? It is basically the same as the interval estimation. So for whatever value, when you calculate it, you find out a sample falls into the confidence interval, then you accept null hypothesis. Suppose it's not the case, it falls out of the interval estimation, then you reject the null hypothesis. Okay? Can I erase it now? Okay, so first we talk about how to test the hypothesis. Generally, there's something you know and there's something you don't know. So that is the reason you want to test it. You know, which one you should believe. So for example, we talked about it before, Vioxx. Okay, it is medicine produced by Merck. And some people say Merck will damage your heart. I mean, the Vioxx will damage your heart. So of course, in this case, you have to do an experiment and to see which way it goes. So let us say if you found out, a lot of people actually, the heart got damaged. If that is the case, then of course, you're going to believe Vioxx is harmful to your heart. But suppose there are not as many people, the heart got damaged, then you're going to believe it is the other case. Okay. Basically, you need to set up an hypothesis. So when doing the hypothesis test, you need to follow these procedures. So in the exam, in the final exam, basically I'll do the same thing. The first step, I will ask you to set up the hypothesis. So what's the hypothesis you need to know, okay? And then determine which kind of value we're going to use. Whether it is mean or it is variance. But in this case, because we haven't talked about anything about the F distribution, so you'll be required to do only the mean. Okay? So basically, you're going to use X bar. So there is nothing quite difficult here. And for the third part, you need to set up a significant level. Significant level is alpha. Okay? Generally, we're going to set up 95% confidence interval. So if significant level is alpha, then the confidence interval is 1 minus alpha. Okay, confidence interval. So generally, we use 5%, and here it will be 95%. Sometimes we're going to set up this 1%, and here it is 99%. So there is nothing special. So we will get you the number. So the question will say, what's the significant level? Say 5% or 1%. And then you're going to find out what's going on in terms of the sample. Okay? The sample we denoted by X bar naught. Okay? X bar naught. And so you want to figure out whether this value falls into the interval. If it falls into the confidence interval, what you're going to do? You're going to believe H naught. If this falls out of the confidence interval, that means it is significant. When we say it is significant, that means it is different. Okay? In that case, you're going to accept H1. That is the alternative hypothesis. Okay, so let's talk about the first step. So generally, you have to set up two hypotheses. The first one is H naught. The second one is H1. H0 is the null hypothesis. And H1, that is we call alternative hypothesis. Okay? And of course, how to deal with it, we're going to talk about the example here. So let us say I'm very concerned about the packaging of drinks. So let us say, orange juice. And of course, when the orange says it is 1 liter, it has 1,000 cc. In that case, of course, I would like to know. Okay, I want to make sure the bottle contains exactly 1,000 cc. Okay, but let us use water. So generally, water it is 600 gram, right? 600 grams. So say mu x is equal to 600. And here, so generally, when you test it, I would like to believe it is this case. But sometimes when it is different, I will say otherwise. Okay? So mu x not equal to. Okay? Okay, and what you're going to do? So in this case, okay? So let us say we use 5% significant level, okay, and 95% confidence interval. And let us say something more. So let us say, x. It is a normal distribution with mean 600 and variance 100. And now n is equal to 25. Even though, in terms of sample size, this is not a large sample size. It has only 25, right? But does it matter? Do we need to use t distribution? We don't, because here it is norm. Sigma x is norm. Okay, sigma x squared is norm. And also, we already know the population is a normal distribution, so we use normal. Okay. So first thing, let us calculate the confidence interval, right? The interval estimation at 95%. Okay. So if this is the case, here you will have 2.5%, right? And the same thing here it is 2.5%. And here it is 600. If you want to construct a 95% confidence interval for this distribution, sample size 25, what is this? So x bar is 600, right? So let us say x bar is 600, okay? Plus, minus. Here, the corresponding z, what is that? 1.96, right? Times square root 100 divided by 25. Okay? Any question to this point? Any question to this point? Okay, so what you get? 600 plus minus. Okay, 3.92, right? Here you got, here 100 divided by 25, you get 4. Square root of 4, you get 2. So here it is this. And so this value is 603.92. And this value is 596.08. Okay? Any questions? Okay. So of course, this is what's going on in terms of the population. But when you take out some sample, right? Is it really in this, in between this value and this value is not necessarily the case. So for example, you take a sample, okay, at a supermarket, and you found out that the x bar naught, that is the average of the sample you get. Okay, this is the sample mean. Okay, when you take a sample and find out the sample mean is equal to 604. Okay, when you take a sample and you find out the sample mean is equal to 604, what you're going to do? Okay, so there are two actions. The first action is A0. A0 is accept, H0, reject, H1. Okay, what about A1? So you have two actions, A0, A1. It is accept, H1, reject, H0. Okay? So basically, this is the options you have. Okay? So when the value fall into this region, okay? When the value you get falls into this region, you're gonna do A0. Okay? You're gonna believe H0. Okay? If it is in this region, that is within the confidence interval, you're going to believe A0. Okay, you believe H0 is right, H0, no hypothesis is right. But if it is out of this region, say here, A1, and here, A1. And what is A1? If it falls out of the confidence interval, you're going to say H1 is correct. H1 is correct. Here you have too much. Here you have too little. If it is too much or too little, what you're going to say? It is not equal to. Okay? Any question to this point? Now we're going to get to right tail test. This is two-tail test. You test two-tail, right? You don't want it to be too much or too little. Okay, so here you have two-tail test. And now we're going to get one-tail test. And first we're going to deal with right-tail test. The same thing. Okay? So in this case, you're going to have the same thing, 600. And here it is alpha. Okay? Remember, when you talk about significant level, when it is one-tail test, here is alpha. When you talk about two-tail test, here it is alpha over 2, right? And here it is alpha over 2. So let us say it is 5% significant level, right? Here, the z you're going to use is 1.96. The z you're going to use here is 1.64 because here it is 5% and here 5%. Okay? So you have to remember, these kind of difference here. Okay. So let us say we use the same thing. Okay? We use the same thing 604, right? So let us say it is 604. And you want to make a decision, see if it is too much. Okay, you want to know if it is too much. So 604, then you want to calculate the corresponding x here. So z is 1.64, but what about this? You want to find out the value, okay, in terms of the, this distribution. So 600 plus 1.64 times 2, right? Because here it is equal to 2. So it is 600 plus 3.28. So it is equal to 603.28. And now, you observe, okay, you take a sample and find out the sample mean is equal to 604. What would you say? You say it is too much, okay? If it is too much, what you going to do? If it is not that much, okay, it's a little bit less, then you're going to believe no hypothesis H0 is right. But because here it is in this region, right? So you're going to see A1. Then you believe H0 is not right. H1 is right. Okay? You accept H1, reject H0. Okay? Okay, the same thing. This is right tail test, okay, because it's at the right hand side. Okay, right tail test. And what is the null hypothesis? The null hypothesis is mu x less than or equal to 600. And the alternative hypothesis, mu x greater than 600. Because if the value is too much, you say it is too much, it's too big. So you're going to believe H1. Okay, not believe H0. Okay? This is right tail test, this is two tail test. And then we're going to get to left tail test. Questions? Any questions so far? Okay, let us try another one. Okay? So let us say now you have something like this. Okay? The same thing is alpha. Okay? And here it is 600. So for this case, what you're going to do, you're going to set up a test of hypothesis H0 is greater than or equal to 600. What about H1? H1 is mu x less than 600. And suppose you observe a value x bar naught that is equal to, let us say, 604. Okay, still 604. Of course, on this side it is equal to, much less than 600, right? So maybe 597, 598, whatever it is. But what you get? You get 604. It is on the other side, right? So what you're going to say? You say, okay, here it is A1 and here it is A0. Okay? So if this is the case, of course you're going to believe, if it is too little, okay, if it's much less, then of course you're going to believe H1 is right. But here is much bigger, right? So you're going to believe H0. Okay, H0 is right. So you accept H0, reject H1. Of course, under different kind of conditions, you may have different kind of results. Okay, so let us try to figure something out here. So here it is 633.28. Because the value is just too close, maybe we try to figure something out. Anyway, okay, so here basically you have three types. The first type, two tail test. The second type, right tail test. The third type, left tail test. And of course, in the question, you need to make your own decision. Which kind of hypothesis you're going to use? Okay, two tail, right tail, left tail. Okay, so this is the decision you have to make. And if we got time, of course, we would like to give you some examples how you tell the difference. Okay, any questions? So let's get back to the hypothesis. We're going to talk about type 1 error and type 2 error. And generally, okay, here, the significant level, it is type 1 error. Okay, this is type 1 error. And we haven't talked about type 2 error yet. So in the exam, you will be required to calculate type 2 error. And what is type 1 error? Type 2 error? Let's get to it now. Questions? Okay. So, what is type 2 error, type 1 error? So you have H0 is right, and H1 is right. And you have two actions. You believe H0 is right, you believe H1 is right. So if H0 is right, and you believe H0 is right, this is correct decision. Okay? But if H0 is right, you believe H1, right? This is alpha, type 1 error. Okay? If H1 is right, you say H0 is right. This is wrong. We call beta. And this is type 2 error. If H1 is right, and you say H1 is right, this is correct decision. Okay? So now, how are we going to deal with this? The point is, we never know what's going on in terms of the actual, the population mean. We don't know that. So as a matter of fact, sometimes we will have to figure out, and generally if I want you to calculate beta, I will give you a different number of the population mean. And from there, you can calculate what's going on. But first of all, we have to try to figure out how to put all these words into a diagram. Okay? That is the most important thing here. Okay. And let us assume now we are doing two-tailed test. Okay, we are doing two-tailed test. And so here it is alpha over 2. Okay, here it is alpha over 2. Okay? And when it is below this critical value, okay, if it is below this value or above this value, what you're going to do? You're going to get A1. If it is on the other side, right, you're going to say, I don't believe H0, I will believe H1. And if it's in this region, what you're going to do? You're going to believe H0. So this is the action you're going to take. Okay? So here you have alpha over 2. Here you have alpha over 2. What is in between? In between, that will be 1 minus alpha. Okay? Okay, so here it is 600. But now let us assume, okay, let us assume the actual mean is equal to 601. Okay, so let us say, as a matter of fact, it is 601 here. Okay? And there is corresponding value here. So here, down here, and here, the same thing, right? Here is the action you take A1, A0, A0, A1. Okay? So let me ask you, what is beta? So here it is alpha over 2, alpha over 2, 1 minus alpha, right? It's very clear. But can anyone tell me where is beta? So on this part, it is H0 is right. Here it is H1 is right. Okay? So then what you're going to get? So here it is, here you assume it is 600, right? But as a matter of fact, how much is it? It is 601. Okay? So as a matter of fact, this is wrong. Okay? But here, when you do this, you assume it is right. But as a matter of fact, it is here. So this one is right. Okay? Suppose this one is the correct decision. The right answer. So suppose this is the right answer. But here, you believe, okay? You believe H0 is right. So as a matter of fact, that's wrong. So what is this? So this is beta. Okay? And what about this part? And this part? So let us say this part is A and this part is equal to B. Okay, so what you're going to get? A plus B, the probability of A plus B is equal to 1 minus beta. Okay? So let us try to calculate beta. Okay, let's try to calculate beta. So let us say, we have the same kind of information. N is equal to 25, and X, it is 600, 100, and so X bar, 604, right? So this is the example going to tell you how to calculate beta. Okay, this is the example how to calculate beta. And also let me show you this. If you're going to decrease alpha, okay, if alpha goes down. So if alpha goes down, what happens? This is going to be very small. But what about here? Very, very large. Okay? Let us take a break. Look at two other cases. That's right tail test and left tail test. So first let us look at right tail test. The same thing we are going to calculate beta. So in this case, okay, let's say it's 600 and that is the same thing 601. Okay? And suppose this is, of course this is the critical value, right? So we're going to get 600. But because this is alpha and we say it is 5%, so now the z is equal to 1.64, right? So then, because it is only one tail, so let's calculate this critical value. This critical value is equal to 600 plus 1.64. And we know that square root of sigma x squared divided by n is equal to 2, right? The critical value is equal to 603.28. And the same thing here. Okay, you want to identify. So because to the left of this critical value, you're going to accept A naught. Okay? You're going to take action A naught. And this is Boolean H naught. And here it is take action A1 and you reject no hypothesis. You reject H naught and accept H1. Okay? So now, can anyone tell me which part is beta? So, Miss Lin, so which part is beta? In this case, which part is beta? So, the same thing, right? H naught right. H1 right. Here you have A naught, A1. Here it is correct, right. Here it is alpha, beta, right. So, which one is beta? You have two choices, right? Which one is beta? This part, right? So, here it is beta. And what about here? 1 minus beta. Okay? So let us do this again. The same thing you're going to get down here is 603.28, right? So you are getting probability of x. So this is beta, right? Probability of x less than 603.28. Okay? And what is this? Corresponding z less than, okay, 603.28 minus 60, how much? The girl next to Miss Lin. So what should be this number? 600 or 601? 601, okay? And this is equal to 2. So again, please help me calculating this number. What is that? PZ less than how much? 1.14, right? 1.14. And what is the probability? Okay, what is this probability? 1.14. Are you sure? Because you are talking about from here to here and also this part, right? So it should be 4.5 plus. So that is 0.8729. Again, you want to be very careful here. The significant level for H naught, it is equal to 5%. But what about the type 2 error? It is 87%, right? So it's very high. So let us try to change the number. So let us say it is still 600, okay? But let us say this is 599. Okay, 599. Okay? The same thing, this is left tail test. Okay, left tail test. And the same thing, 5%. So it is 596.72. Okay? And down here it is 596.72. Okay, the girl behind me did. So what? So where is alpha? So this is alpha, right? And A1. And here A naught. And here it is 1 minus alpha. Okay? So where is beta? Where is beta? This side, right? Okay. Here it is 1 minus beta. Okay, the same thing, you are required to calculate beta. So then, this is 599. Okay? P of x greater than 596.72. Okay? And then z greater than, okay, the girl in blue coat. So what is here? How to put down the formula here? What's the number I need to put in? (596.72) minus 599 divided by 2. Okay? So can someone help me with this number again? P greater than negative 1.14. Are you sure? Okay? And so here, because you have 1.14 here, right? So the probability is equal to 0.8729 again, right? Questions? Okay, so from here, you know, there are a lot of calculations. First of all, you need to identify which kind of test. Two-tailed test, left-tailed test, right-tailed test. Okay? Then the second one, you want to be able to get from the sample value to make a decision. Say, if you want to believe H naught or believe H1, okay, alternative hypothesis or null hypothesis. And then you will be required to calculate beta. So basically for the final, okay, the most important thing is the interval estimation for two populations, okay, and then the interval estimation for variance, okay, and of course the interval estimation for the differences of two population mean. You have several conditions. The first condition is independent, sigma x, y known, okay, sigma x squared, sigma y squared known. The second one, independent, but sigma x squared, sigma y squared unknown, but we know that sigma x squared is equal to sigma y squared. Okay? And also, there is something that, you know, when the two populations are not independent, so you need to use pair, okay, sampling, okay? Then you have to get a new variable called d. Di is equal to xi minus yi. And then you get to variance estimation. Okay, interval estimation for the variance. We just talked about it, right? When mu is a known, okay, when you don't know anything about mu, then you use Sx squared. If you know mean, then you use sigma head squared. Okay? The reason we use sigma head squared because it is an unbiased estimator for population variance. Okay, and then we get to the hypothesis test part. Okay, so basically that's what we're going to have for the final. And for next week, we're going to get some examples, discuss it, and do some calculations. Okay, and then there will be for the semester. But okay, the most important thing for this class is for you to pass. And some of you, okay, haven't done quite well, and you need to be very careful about it. So constant practice makes perfect. So you need to do more problems. See you next week.